The following program is brought to you by Caltech.
Okay, it is a true pleasure and honor to introduce Dr. Harold McGee. Dr. McGee's first and most famous book on food and cooking, The Science and Lore of the Kitchen, is actually the textbook for my class at Caltech, as we heard PA 16, Cooking Basics. I can guarantee that at least 75 Caltech students a year read this book. And actually, they also get to play with Rotovaps, anti-griddles, sous vides, vacuums, you name it. Dr. McGee graduated from Caltech with a BS in literature in 1973. He earned his PhD from Yale in 1978. His first book on food and cooking was first published in 1984 and was fully revised in the year 2004. In 1990, he published The Curious Cook, More Kitchen Science and Lore. In 2010, he released Keys to Good Cooking, a guide to making the best of foods and recipes. Dr. McGee has been published extensively in journals and magazines and writes a column for the New York Times. He is seen frequently on television and has collaborated with some of the best chefs in the world, including my favorite, Thomas Keller. Any chef and aspiring chef should have at least one book by Dr. McGee on his or her reading list and bookshelf. I certainly would consider his first book the single most important piece of literature in cooking and food. The days when chefs and cooks were learned by repetition alone have long since passed in favor of a need for a broad understanding of the scientific principles behind all of the processes in the kitchen. At Caltech, our students are going to want to know why a souffle rises, why does a banana turn black in the refrigerator, and what happens to lettuce when you cut it with a knife rather than tear it. Most importantly, they are going to want to understand all of the basics so that they can create and not copy. Thus, I present to you the man who is not only bringing science to cooks of all types, but is bringing our students and scientists to cooking. Harold McGee.
Thank you, Tom. That was beautiful. Thank you. Let's see, button one. And there we go. Okay. It's a great pleasure to be here and an honor. And what I want to do is speak with you briefly, because lunchtime is coming, about this recently reinvigorated conversation between science and technology and cooking, which I was very lucky to stumble on a long time ago, 30 years or so ago. Right around the time that it was beginning again. It does go way back into history, and I'll show you a bit of that. This class that Tom teaches is an example of this reinvigoration of the conversation between these two disciplines. Tom teaches regularly for Stephen Hawking on his visits to campus, and you've heard about the kinds of things that go on in the course. When I was here in the early 70s, we didn't have a course like that, so we had to kind of do it ourselves. I was in Blacker House, and yes, in 1970 or so, the then president, Eric Schiff, instituted something that he called the Posh Dinner Parties. And we prepared them ourselves in the basement in the Blacker House kitchens, and then would schlep things over to the Athenaeum, which was closed on Saturdays at that time, and we would have the meals there with wines, cigars afterwards, the whole thing. The first year that we held it, it was pouring rain, and so we took everything over, including the diners, through the steam tunnels. But it wasn't anything like the adventure in science and technology that Tom's students get to experience. So what I want to do is just give you a very quick history of this conversation, a little bit about what I did, and then some of the wonderful things that are happening these days, in fact, this year, in this field. Scientists and cooks have been talking to each other for a very long time. This is by no means the first example, but it's one of the most prominent. Denis Papin was a member of the Royal Society at the same time that Isaac Newton was. He worked with Robert Boyle. This is around the time that the gas laws were being understood. And so he came up with what we're usually taught in school, the first version of a steam engine, but he also came up with the pressure cooker. And this is it's not the original, this is an advanced, I think, 18th century version of the pressure cooker. He was working in the 17th century. And back then, in the Royal Society, most of the members were bachelors. They would get together at each other's quarters for dinner together, and sometimes they would do it in the 17th century equivalent of a Tupperware party. They would cook everything in Papin's digesters, and we have diary entries that give us a clue of the excitement that they had when they experienced foods that had been cooked in a way that had never seen the light of day before. So this is John Evelyn's diary. Everything was cooked in Monsieur Papin's digesters, by which the hardest bones of beef itself and mutton were made as soft as cheese, without water or any other liquor, and with less than 8 ounces of coals, very energy efficient, producing an incredible quantity of gravy, and for close of all, a jelly made of the bones of beef, the best for clearness and good relish, and the most delicious I've ever seen or tasted. Then we ate pike and other fish, bones and all, without impediment. And even better, nothing exceeded the pigeons, which tasted just as if baked in a pie. So you could just get this sense of discovery. This is a new world of food and cooking opening up way, way back, thanks to science. In the 18th century, same thing. This little illustration appeared in a book about life in general, and it's difficult to see the French ditty at the bottom, but you see it's a woman at the stove working, and the little poem introduces the term nouvelle cuisine in the 18th century. We think of nouvelle cuisine as something that developed in the 1970s. Here it is a couple centuries before that. Every year there's nouvelle cuisine because people's tastes change, and so you have to be a chemist. You have to know your materials. You have to come up with new compounds, new permutations and combinations. You have to think about what you're doing. Fast forward to my life. I'm one of those people Cleve mentioned who studied at Caltech and then went off and wrote. I ended up not writing about Keats, which is what I thought I would end up writing about, but about cooking for a variety of reasons I can tell you about some other time. I wrote this book without really knowing that much about food, and so I would look at the classics to see what it is that I should write about and what I should try to explain. One of those books, the current one at the time, was Julia Child's Mastering the Art of French Cooking. And one of the things that Julia Child says is that when you're making meringues or soufflés, you should use a copper bowl, because copper acidifies the egg whites and gives you a better foam. And I remembered enough chemistry to know that copper ions are not going to change the pH, at least directly, of a protein solution. So I thought this was, crazy old cook's tale and didn't think more about it until I was looking for free illustrations for my book, illustrations I didn't have to pay for, which means old illustrations. And I came across the following, an illustration of a pastry kitchen from the 18th century in France. And you can see over here, there's a boy clearly whipping something in a bowl. And this came with a key, and the key said that he was whipping egg whites in a copper bowl to make biscuits. So I thought, okay, if Julia Child says so, and they were doing it 200 years ago, maybe I should take a look. And this was my introduction to the importance of doing experiments in understanding food and cooking. Up to that point, I was just taking what I read in journals like Poultry Science as gospel, but I realized after this that there was much more to explore. I did the experiment. I whipped egg whites and copper and glass side by side and found a tremendous difference in color, in texture, in the rapidity with which the foam drained, everything. So I left Caltech with a Bachelor of Science degree in English, and then 15 or less than that, a few years later, I ended up publishing a paper in Nature, because this was, as far as I could tell, an undescribed phenomenon. I talked with protein chemists. They didn't have an answer for me, so I found a couple of like-minded scientists, including Sharon Long, also of the class of '73, Blacker House. You can't really see it, but we used the spectrophotometer to see what changed when we whipped with copper ions, sent the manuscript off to Nature. They put it through their usual review process, and we got positive reviews with one negative comment. One of the reviewers said, the science is fine, the subject is fluffy. So I wrote that book. It got some interest. I wrote another book, and this was more not explaining cooking in kind of factual terms, but describing experiments. It's more of a narrative book, mysteries and how I tried to understand them. One of those mysteries brought me, in my mind, back to Caltech, because I recognized at a certain point, I don't remember exactly when, that when I'm frying, and I make a spattery mess all over the place, including on my eyeglasses. For some reason, on my eyeglasses, the spatter ends up not on the outside, but on the inside of the glasses. And that didn't make any sense to me. Here's the spatter coming at me, and somehow it's making this detour around to the back side. So that really bothered me. And I started thinking, oil droplets and strange behavior and moving and Millikan, and right? The oil drop experiment. So I thought maybe there's something funny about the electrical field around the head of a cook that is causing these charged oil droplets to move in strange ways. So I made myself masks of Agamemnon out of aluminum foil, tried to ground myself to change. Nothing made a difference. So that then really bothered me, and I decided I had to figure it out. So I set up a system of detectors. And worked very hard at changing all the parameters I possibly could, and finally figured it out. And unfortunately, it wasn't as interesting. There was no reason to go into the Mask of Agamemnon business, because it turned out that it was just geometry. My thought was that as you're cooking and the spatter is going like this, it's going to end up on your glasses. But it turns out, actually, most of it goes straight up in the air and then slowly rains down. And because you're looking down at the frying pan, it's all ending up there. So that's back spattering in frying. A few years after that, I was invited by, again, English major, invited by Physics Today to contribute an article to a special issue they were doing on the science of everyday life, the physics of everyday life. So I got to talking with a couple of friends of mine who were I live in the San Francisco area, a couple of friends who were in the silicon chip fabrication business. And they had some software. This is 1995 or so it wasn't MATLAB. I wish we'd had it. They had some software for modeling heat transfer in silicon chips. And so we adapted it to model heat transfer in meat, in cooking, and published this kind of review of how it works and ways that you don't ordinarily expect. But one of the great things you can do with a computer is have it do experiments that you yourself would never do, because it's just too crazy. And one of the questions came up was, when you're making a steak or a hamburger, does it matter how often you flip the burger or the steak on the grill? And so we just had the software flip once during the cooking, twice during the cooking, and then, because we found some interesting stuff, every 15 seconds. And it turns out that the faster you flip, the more even the cross-section, so you end up with a more even doneness on the inside. And again, you can't really see it, but the cooking time goes way down from, it's like 10 or 12 minutes here to maybe 7 when you flip almost constantly. That was what the computer was saying. The question is that real? And so, but having seen it, I got myself some steaks, and I put a thermocouple in the middle, and I stood there flipping, and sure enough, it works. and that helped us understand how rotisseries work. And anyway, it was a wonderful discovery, not the most practical, but if you want to get steak done really quickly, flip it frequently. I'm going to shift from the stuff that I've done to talk about what's happening in the professional food world these days, the world of restaurants. I showed a slide earlier on, nouvelle cuisine in the 18th century. I'm going to jump ahead now to the 1990s. This is a man who was very important in the kind of aftermath of the nouvelle cuisine of the 20th century. To show you what counted as nouvelle cuisine in the 1990s as innovation. On the left is a salad for which he was very famous, and the reason this was a remarkable achievement was that in classic French cooking, you had one or two ingredients prepared perfectly, and that was it, with an appropriate dressing. This man, Michel Bras, lives in the countryside, and he decided he was going to go out every day and find edible wild stuff near the restaurant and incorporate that into his salad, and that would make it much more particular to his place in his restaurant. That was an idea that hadn't occurred to people before, and it has had a tremendous influence. The other thing he came up with that maybe you're more familiar with, or probably more interested in, is the molten chocolate cake, which is in the lower right-hand corner, in which he took a nugget of ganache, chocolate and cream, froze it, and then put it inside a biscuit dough, and then cooked that just perfectly so that by the time that the outside was cooked through, the ganache interior was melting. That's something that, again, was a kind of engineering feat that had not been attempted before, and just thinking that way was a very different sort of thing. So that was nouvelle cuisine in the 1990s. Now we're 2003, 2004, the nouvelle cuisine. Because this man came along, and this is the man who really made it fashionable to bring science into the kitchen. His name is Ferran Adria. He has a restaurant in Spain, which is going to close in July, because he's been doing this for quite a while, and it's not an easy thing to do. It occurred to him in the late 80s. Tom, in fact, quoted his mantra, to be creative is to not copy. And he took that to mean not just don't copy other cooks, don't copy myself. So he set himself the task of coming up with completely new dishes every year. And science is a very useful thing to have in your corner when you have to innovate in that sort of way. So he's the one who really put it on the map. And this is his version of nouvelle cuisine. So and he, in fact, modeled it on Michel Bras' salad, but instead of it being lots of different ingredients that are growing around the restaurant, it's taking familiar ingredients and turning them into something that you can't recognize. So you see these things, you have no idea what they taste like. You have a vague idea of what they might be. There's beet, there's tomato, there's peach, there's corn, unusual combinations, but you can't immediately tell what it is that you're going to experience. And that's exactly what he wants to do, is not satisfy your expectations, but defy them and come up with things that you would never have been able to imagine in the first place. In order to do this, he did something really revolutionary. In the time of Michel Bras, and probably for many people still, the idea of using molecules, pure compounds that had been developed for industry to stabilize things, to preserve things, and so on, to use those in a fine dining restaurant would have been abhorrent, and people just wouldn't do it. The way Ferran Adria looked at things was, I don't care how these things have been used in the past, can I do something interesting with them? And so he took those same industrial ingredients, xanthan gum, carrageenan, alginates, things like that, found really interesting things that you can do in fine dining with them, and then repackaged them into what looks like a line of cosmetics or something. He made them chic in a way that still amazes me. So here are some examples of the things that he's done with them and that other people have done with them. This is a rethinking of the ravioli. Ravioli is, there's interesting stuff inside and a nice sauce on the outside, but the container itself, the envelope, is just dough. So he thought, well, why not make it more interesting? Why not make it transparent so you can see what's inside? And then why don't we give it flavor? And so he found a way of combining several different thickeners in just the right proportions that you could make a transparent, flexible, heat-stable envelope, and then made with it dishes like this, which I think it's gorgeous, and it's delicious. You'll have to take my word for that, but I think you can see that it's gorgeous. Completely, and that's such a different approach to cooking than had been taken before. Take a traditional thing and then make it much more interesting by rethinking it from the bottom up. He came up with an idea for what he calls caviar, in which he can make caviar-like things, that is to say, little bubbles with a very flavorful liquid on the inside and a skin on the outside, so that when you put it in your mouth, it pops and delivers this punch of flavor. He found a way to do that for any liquid by using alginates, a seaweed carbohydrate, which gel only in the presence of calcium. So you make droplets of whatever liquid that you want with a little bit of alginate in it into a water bath that contains calcium, and it begins to gel from the outside in. And that's shown in the upper right-hand corner. So you can control the thickness of the shell, the consistency of the bubble by how long it stays, and then when you take it out and when you rinse it. So you can make caviar. This is melon caviar. You can make caviar of any flavorful liquid you like. A wonderful inventive chef in New York took this a step further and said, okay, caviar is nice, fish eggs. How about eggs? So this looks like a sunny side up egg. In fact, it's not. It's completely constructed with these thickeners that Ferran Adria has introduced into the restaurant world. So what looks like the white is actually a gel of coconut milk. And the yolk, which you can see it's a little suspicious because it has air bubbles inside it, but when you cut it, it flows just like an egg yolk does. Turns out to be flavored with carrot. It's a large carrot caviar. So you are presented with this plate that looks like a fried egg or a sunny side up egg, and it ends up tasting completely different. That combination was meant to shock, which it does. A really delicious version was the white is mozzarella and the yolk is golden tomato. That was a nice one. Using yet another thickener, Gellan, Heston Blumenthal, who's a chef in England, came up with a way of making a cup of tea that is hot and cold at the same time. So what he does is he makes tea with this thickener, gels it, and then purees it, so he has what's called a fluid gel. It pours, but it has a viscosity. But you don't notice any particles. And then he puts a divider into this cup and then pours hot and cold on both sides, lifts out the divider, and they're viscous enough that they maintain that temperature differential long enough for them to serve it. And that's a very weird experience, putting something hot and cold in it. But you have to drink it in a very particular way, right along the correct axis. A very different magic powder. These industrial ingredients are often referred to by the chefs as magic powders because it means they can do things they couldn't do before. Another one, very different one though, not a thickener, is transglutaminase, which is an enzyme that cross-links proteins. So you can use it instead of protease, which breaks things apart, in which we have, for example, meat tenderizer has an enzyme that breaks proteins apart. This is an enzyme that joins proteins together, which means you can take proteinaceous materials and do things to them that you couldn't do before. So Wiley Dufresne, again, in the bottom left, has done his ultimate chicken McNugget. It's breast on the inside, surrounded by a shell of leg meat, surrounded by a piece of skin, and all perfectly cooked because he's put the most heat-sensitive one in the center and the one that needs to be browned on the outside. In the lower right, that's surf and turf, but the fish and the meat have been joined together. It's pork skin around salmon. And then above that, what look like noodles, and are in fact noodles, are actually noodles that are made out of pure shrimp. He purees shrimp, adds a little bit of this enzyme to cause the proteins to bond to each other, then extrudes them, puts them in boiling water, and you end up with noodles that are nothing but shrimp and a little bit of that enzyme. And then this is kind of far-out version of the same idea. There's a metalworking technique that's meant to imitate wood grain, and these cooks have taken the enzyme, lamb, and yellowtail, a fish, and sliced the fish and the lamb very thinly, glued them together, put them on a funny kind of surface, frozen them, and then cut them very thinly. So this is a tartare of lamb and fish in a beautiful pattern. Now, getting to something that's maybe a little more useful to home cooks, temperature control. Cooking is all about temperature, and it's only very, very recently, and still very expensively, that we can really control temperature accurately in the kitchen. So, labs have had water baths for decades, and they're only very slowly trickling into the home and restaurant kitchens, although these days most restaurants now have them. This is an immersion circulator, which you can put into a pot, so it measures the temperature, heats the water, and also circulates it so that you don't end up with dead spots, boundary effects, and that kind of thing. And this is a domestic version of the same thing, but it's several $100s, which is crazy, but that's what it is at the moment. Anyway, it's very useful because you can set the temperature by the degree, 140, 141, 142, and that's what it keeps it at. And it's fantastic because it's opened up, in a way, the same unknown world that the tasters of Denis Papin's digested foods were experiencing. We're seeing things that we haven't seen before because we never had the control over these phase changes that take place in these foods. So if you take an egg and you cook it at 1 degree intervals, 1 degree centigrade intervals, these are the different consistencies you get. And between 60 degrees and 67 degrees or so, pretty much every degree gives you a different texture. And so you go to some restaurants nowadays and they'll say that they're serving you a frisee salad with a 63-degree egg. And that's because each chef has his or her own favorite consistency in eggs. In some of these, the yolk has the consistency of a pastry dough so that you can roll it out and form it into containers and things like that. Nobody had any idea because no one was able to control the temperature that precisely. Same thing with fish texture. Every degree makes a difference. And so my friends at the French Culinary Institute have done a series of these experiments, degree by degree tests. And then we sit down together and we taste them and we see what we think. And we found that in the case of salmon, this is salmon in particular, and every fish is different, there are a couple of zones where the texture is very nice, and then other zones where it's not, and it's not just that it's overcooked. Between 40 and, 50, what's called here toothy means it sticks. You chew on the salmon and your teeth stick together in a not very nice way. And as far as I know, no meat scientist or fish scientist has looked into what's going on. in that temperature range. So things to discover. And then you can do things with meat. This is, wow, on a big screen, that's really something. This is a short rib. Usually you cook short ribs to like 180 degrees or something like that Fahrenheit to soften the connective tissue and make it succulent, which means that it's well done. But with this temperature control, what you can do is cook that same piece of meat at a lower temperature for a longer time to cause the connective tissue to dissolve. And so this is a short rib that's been cooked for 2 days at 138 degrees Fahrenheit. It is soft, it is tender, but it has a texture completely different from a standard short rib. You can still see that there's intact connective tissue, this line here, and the fat tissue is still intact, which means that all the parts of the meat are soft, but they're all still in their regular places. They haven't kind of melted into each other. And that's a very different experience of a short rib compared to the usual. Tom mentioned that they have a Rotovap in the Caltech cooking lab. And Rotovap, rotary evaporator, is a way of doing distillation, that is to say, the removal of aromatic materials from the matrix, the flavors of foods from the foods themselves, at relatively low temperatures so that you don't change the flavors very much. Distillation goes way, way back. You do it every time that you leave the lid ajar on a pot of boiling whatever. The water that collects at the top there, the liquid, is concentrated in aroma because the aroma has been evaporating off. This is a machine for doing that very efficiently and particularly. And some chefs have done wonderful things with this. You're essentially taking aromas from the foods and turning them into a concentrate, which has no texture, no color, just flavor. So this is a pastry chef who presents you with a dessert of all white things, jellies and creams and sorbets and so on and so on. They all look like they're maybe lemon or champagne or something like that. But in fact, one of them tastes like chocolate, one of them tastes like coffee, one of them tastes like passion fruit, all things with very, very intense flavors, but you have no clue looking at it exactly what they are. And the experience of those flavors in the absence of the color cue is a very different experience from what we're used to. An especially imaginative use of this technique was this dish. You can't quite see, this is a glass block that the thing is served on. That's an oyster, and then around the oyster is a jelly. And so you just, in a spoon, get the whole thing and plop it in your mouth. And the oyster tastes like an oyster. The jelly, it turns out, when I first tried it, I couldn't place that flavor at all. It had a distinct flavor, but I couldn't figure out what it was. And then finally it sort of became clear. It was the flavor of earth. It was like eating an oyster while you're walking through the forest and smelling the forest. And what this guy had done is take a handful of forest soil and distilled it, gotten off the aroma of the earth, and then put it in that jelly. Any of you who know about environmental analysis, that's a worrisome thing, to be eating the distillate of dirt. But if you only do it once in a while, it's probably okay. The guys at the French Culinary Institute are especially interested in understanding what's going on in cooking so that they can better teach their students. And one of their passions is cocktails. And there's a lot of lore out there about the importance of the way you shake, the size of the ice cubes, the brand of the ice cubes. Some ice cube makers say that their ice cubes come out colder than other ice cubes. So there's a lot of mystery around this, and so they decided they were going to do a serious job of figuring it out. So they put a thermocouple, embedded a thermocouple in the bottom of a shaker, and then invited 3 of New York's, or actually 2 of New York's best bartenders, and then one of the experimenters, who refers to himself as the crazy monkey, because he doesn't have a special way of shaking. And what they found was that doesn't matter who's shaking, doesn't matter how hard you shake, doesn't matter what ice you use, it all cools down the same way. And then to a book that has just come out this year, or a series of books, came out in March. A really remarkable kind of summa of what it is that we know about the science of food and cooking at this point. And a lot has been going on in the last few years. It was masterminded by the man at the right. It involved a team of 15 or 20 people working for several years. And the gentleman at the right was able to do this because of his past. His name is Nathan Myhrvold. He was the chief technology officer at Microsoft for many years. He has always loved food and cooking. In fact, he took 2 leaves from being chief technology officer. The first one to go to France to study cooking, and the second one to work in a Seattle restaurant on the line, just cooking. So he's always had this abiding love and interest in it. When he left Microsoft, he then had the time and opportunity and resources to do something serious about it. And so he's put together this amazing compendium of what we understand at this moment about the science of food and cooking. It was done in, well, it's hard to imagine this being a kitchen. You can see, you know, there's a mixer, there's a wok, a garbage can, but this, for example, is an extremely large rotary evaporator, much larger, I'm sure, than the one Tom has. It's tricked out with everything you would ever want, including a machine shop, so that they could show exactly what's going on inside various appliances as they're working. So, this is the introduction to the chapter on heat. And remember, this is a book that is intended for professional cooks. I'm sure he's happy for physicists to buy it as well, but this is intended for cooks, which shows you that, of course, he doesn't expect people to remember this equation, but he wants them to know that if you want to really understand heat, there is this body of knowledge that you can draw on. And then he's done these remarkable cutaway illustrations where they have taken a Weber grill and sawed it in half, and then worked very hard with minimal photoshopping, actually, to show you what's going on during the cooking process and to annotate it. And that's a sample, not really that legible, to show what's happening in the different areas surrounding the coals. On the coal surface itself, in the vapor above it, in the flames, exactly what's happening in those different zones and their influence on the cooking. And he has, for example, graphical aids to figure out what is the sweet spot on your grill. And he defines the sweet spot very precisely as that area in which the heat transfer is plus or minus 10% within plus or minus 10% of the average. And so you can take your grill, make measurements, and figure out where it is that you want to keep things if you want to keep them cooking at about the same rate. He's found that it makes a difference, of course, how high above you are, the size of the grill itself, and if you take aluminum foil and line the interior of your grill, the side, that can essentially bring the sweet spot out to the edge of the grill itself all the way. Finally, back to science and cooking and education and universities and institutes. Harvard University last year, for the first time, gave a course in science and cooking from haute cuisine to soft matter science. They invited about 10 chefs, Ferran Adria among them, so that's him on the left, back when he was not exactly an enfant terrible, but much younger. And then on the right, lecturing at Harvard. So they brought chefs in to give lectures, and then they explain the science of what's going on. The two people who came up with this course have been teaching general education science courses at Harvard for, I don't know, 15 years or something like that. They told me that they would get 15 or 20 students, and then by the end of the course, they'd have maybe 7 or 8, and it was a real struggle. They announced this course expecting they would maybe get 100 because, you know, it's a kind of popular thing. They had 700 applicants, and they were able in the end to take half of them. So they taught the course for 350 people. And it was, as courses like that go, a serious course. So they had equations, students had equations to understand. The professor in the course, Dave Waits, said, don't leave the slide up on the screen for very long, because many of these are kind of approximations. They're meant to help freshmen understand what enthalpy is, what entropy is, what the balance between the two has to do with anything. A little bit about protein denaturation, heat transfer, and that sort of thing. So they're meant to be teaching devices rather than truly accurate descriptions of what's going on. But it means that the students become acquainted with the idea of working with equations like that. They have an equation of the week. So this is the heat transfer equation, and they do experiments in lab to understand what's going on. But they also have a recipe of the week. And so they go into the lab and they cook something that in some way or other represents what it is that's going on in the equation of the week. So this is Michel Bras' melting chocolate cake. They've done it very differently. Instead of taking a nugget of ganache and then doing some complicated manipulations to it, they simply undercooked a cake batter and figuring out how long it should cook, at what rate that boundary changes from the hardened to the liquid. That was the object of the exercise. But of course, at the end, you get to eat it. So that's the kind of thing that's going on these days. I think it's really interesting times for both sides, for the science of soft matter and for cooks. New worlds are opening up every day. So with that, I think it's lunchtime. Thank you very much.